Hi guys, today's video is an exciting one. It's on forces, so part of the applications of vectors topic, which a lot of people would consider to be one of the, if not the hardest topic in all of extension 1. Generally speaking, the applications of vectors topic contains forces and velocity as it relates to vectors, and also projectile motion. So over the next coming weeks, I'll do some videos on projectile motions in the 3-unit context. So for those that have already subscribed to my channel, I've already done some videos as for projectile motions as it relates to 4-unit extension 2. So have a look at those videos if you're doing extension 2. But over the next few weeks, I'll do extension 1 projectile motion. So without further ado, let's do some forces. So with forces, it used to be purely on a topic that is contained in the extension 2 4-unit topic, but as part of the rejig of the new syllabus, a lot of these forces are now put into and vectors is put into the extension 1 topic. So what we're going to do today, I've got 4 examples to go through, and there's not a lot of theory per se because it just relates to Newton's second law, F equals ma. That's really the theory behind it, and it's just 4 illustrative examples to get us going. So, also with these illustrative examples, just to, in the interest of time, I won't write out all the words. I'll give you the diagram and I'll just describe them to you. It should be fairly similar to a majority of the questions in the textbook and the past papers anyway. So just to be absolutely clear, when I start this, color, let's start with this guy. So forces with vectors. Yep. So everything relates to Newton's second law of motion, and that is F equals to ma, and that is big, right? So basically with this very simple formula, it basically helps us describe motion and forces in this topic. So that's it for theory. Let's dive into a few illustrative examples. So basically there's sort of 2 buckets of questions almost. There's ones that basically relate to strings where objects are suspended or part of a pulley system. And then there are questions that have objects that are either suspended or moving as part of a pulley system on an inclined plane. So generally speaking, they're either suspended, right, or part of an inclined plane, part of like a triangle when an object sort of slides up and down the incline. So I'll start off 2 questions. Maybe the first one is relatively straightforward. Let me draw the diagram. It's basically a pulley system. So pulley system, there's my pulley, right? And there's a double hanging weight. Let's say there's a smaller weight on this side and there's a bigger weight on this side. Now, all else being equal, right, if you have one weight bigger than the other on a smooth pulley system with strings that are doesn't have any weight in them, generally speaking, if it's heavy on one side, the system will move towards that side and give us an acceleration. So just on this diagram, I'm just going to give you a little bit of acceleration. So let's say this acceleration is 6 meters per second squared into the direction of the heavier weight, right? Let's give maybe this smaller weight 5 kilograms. Yep, and let's say this one here is missing an m kilogram, right? And also then in this string would be a common tension because it's part of the same string, it's connected. So let's say that tension there is T and T. And let's say this question then is find the value of T and the mass of M. Yeah, so quite straightforward. And maybe where possible, let's just do it to 1 dp. Right, a very simple diagram. So there's a pulley system, heavy on one side, lighter on the other. Now, how do you know it's heavier? Well, it's moving in that direction, so it generally implies that it's heavy unless the string has weight. In this case, it doesn't, so ignore that. So if your teacher was to give you this question, obviously there's a whole paragraph of text, so I'm just going to cut that out to save some time. So the best way to do questions like this is to label all the forces onto here. Now, what I haven't got here right now is the forces relating to gravity and It's naughty of me. Can you let's just do this as a general, right? So general across all 4 questions. So if I don't tell you otherwise, gravity is 9.8 meters per second squared, right? I'm just going to put that up there just so we can avoid writing it over and over. So in this question here, the missing forces at play is there's a gravity aspect there where it's mg, right? So m in this case is 5 times 9.8 going downwards, right? And this one here would be mg there as well. So I'm going to do 2 things, right? I'm going to resolve the forces on this one and then resolve the forces on this one. By resolve, I mean by comparing it to get a resultant force using Newton's second law of MA. Now, in the first mass, so let me decompose that. So the first mass looks like this. There is a tension on top of T, and there is a gravity aspect of 5 multiplied by 9.8. And I know there is a resultant force that is dragging it upwards at an acceleration of 6 of MA, right? Where in this case, acceleration is 6 and the mass is 5. Yep. So in this case, if I resolve forces, I know that MA equals to tension, right? Because they're both pointing upwards. Tension's positive. The gravity force is negative. So 5 times 9.8, right? Sub in my 5 times acceleration of 6 equals to T minus 5, 9.8. I can do tension then equals to 5 times 6 plus 5.9.8, right? Get the value of tension quite easily. So let's see if you did on your calculator. I'm hoping it's like 79 newtons. Now, if my arithmetic there is wrong, please bear with me, but the concept there hopefully is sound that the tension there is 79 newtons. Pretty easy. Now, once you get the tension on one string, use that tension on the other to find the missing mass, right? So using my bigger mass, my bigger weight, right? I've got tension pointing upwards still, right? Remember, tension is pointing at each other. In this case, I got gravity force of mg pointing downwards. And then my resultant force, though, because the pulley system is moving towards a bigger mass, this is my new MA. And what you got to be taking into account here is that that mass there is different to this mass here, right? It's on the bigger mass in this case, and the bigger mass is missing right now. So using the second heavier weight, MA equals to, now because they're both pointing downwards, gravity force is bigger in this case, minus tension. So what I would do, because M is missing, I'm going to move, maybe I'll move T on this side, move T to the left and MA to the right, just because T is positive that side. So then T equals to, I'll factorize out the M, it'd be gravity minus acceleration, right? So sub in my 79 here, my mass is still missing, but that's 9.8 minus acceleration of 6, is 3.8. If you did 79 divided by 3.8, let me just quickly whip that up into the calculator. Divide by 3.8, should get 20. You guys get 20.8 kilograms. So very, very much a heavier weight on that side to cause that level of acceleration. So that's resolving forces to basically find the variables of tension and mass that I want. Hopefully that's okay. That's our first illustrative example. So a pulley system that has movement in one direction based on the fact that that one mass is heavier than the other. So another one. So the next one has a bit more. It's a bit more involved because there's 2 tensions, but it's a very common question indeed. So make sure you can do something like this. So instead of just having one mass hanging from one string with one tension, let's suspend it in the air with respect to 2 strings, right? So a very common question. So this is, picture this to be the ceiling, and we have a mass, right, sitting suspended in air. Let's say this mass is 20 kilograms in mass. And on one string, which ties itself to the ceiling, it's at 45 degrees to the horizontal, and the other, it's tied itself at 30 degrees, right? And let's pretend that this is currently suspended in air. In other words, the forces have all sort of cancelled each other out and it's just holding on in there. So when you do this, the question would basically, if it doesn't tell you, you should know yourself because the angles are different. That would have tension 1 and that would have tension 2, right? For it to remain stationary in air. So obviously then in this case, maybe the generally speaking, the question would be find T1 and T2 to 1 decimal place, just like before. Now, obviously, once again, let's assume gravity of 9.8. What's missing from this diagram is the additional element that there is a gravitational pull of mg going downwards. So that's 20 times 9.8. I'll label that in my diagram. But so when you get a question like this, a very smart idea is to basically decompose your forces into all those that are vertical and all those that are horizontal and compare it. Now, if they're suspended, if the object is suspended in air, then the resultant force of ma is 0, right? There is no acceleration that is applied that has the object does not have acceleration, right? It's stationary. So what that means is the sum of all vertical forces will be 0. All the positives cancel out with negatives, and all the horizontal forces cancel out to 0 as well. So this is what I'm going to do. All right. Firstly, I'm going to draw the right angle triangle on the left and the right to basically identify all the forces that I need. So for the right angle triangle on the left, sorry, with a 30-degree angle here, this is tension of T1. Yep. So ignoring the weight for now, I just want to get the expressions for maybe I use green for this vector here and this vector here, right? Because the sum of the two greens give me the resultant black in this case. Now, using Sokotoa, I know that sine this guy equals the opposite on this guy. Rearranging that, this guy here is going to be T1 sine 30, right? And similarly, I'll leave I know sine 30 is a half, but I'll leave sine 30 as part of your working out there because theoretically, if that was 20 degrees, I could do the same sort of working out. So this is usable for any angles with any two angles that are different, right? So this one here using Sokotoa would be T1 cos 30 as well. So I'll leave that there. I'll simplify it later. Now, so the two greens make up this T1 force. And similarly, I have a tension of T2 there. That's 45 degrees there, which is nice. I mean, I don't really need Sokotoa per se. I'll use Pythagoras if I really want to, but let's just use Sokotoa. Now, let's use a different colored pen. I'll use a red one here in this case. So to basically decompose that into red plus red equals to black, using Sokotoa or using Pythagoras if you want to. That's T2 sine 45. Using this angle here, you don't really need that 45 there. So T2 cos 45 as well. Perfect. You know what? Just to avoid ambiguity, I'm just going to remove this 45. Yeah, just to let you know that I'm using the one upstairs. All right. I've got the greens, I've got the reds. That decomposes my diagonal forces into vertical and horizontal. And I'm now going to compare it to the mass of gravity, right? So let's start with vertically. Yeah. If I compare my vertical forces, what's there? There's this green one pointing up, there's this red one pointing up, and then this other green one pointing down, right? They all net to 0. So it doesn't matter which one you call positive because it nets to 0, it doesn't matter. So let's just call the ones going upwards 0. So T1 sine 30 plus T2 sine 45. They're the two pointing upwards minus my gravity force. That should give me 0, right? Net force equals 0 because it's stationary. Let's sub in everything, right? So I got T1. I don't have T1 yet. I got this exact value to be a half. I got T2, that exact value to be root 2 on 2 minus the mass of 20 times gravity. Perfect. Right. So how about we times everything by 2 and then move this guy over as well? Therefore, I got T1 plus root 2 T2 equaling, let's see, is it now? I'll do this quickly on my calculator, just 20 times 9.8 and then multiply by 392. That's good. I have my first equation to solve simultaneously, right? From the verticals. Now, when I resolve the forces horizontally, I should get my other equation to solve simultaneously. Let's see. So horizontally, I've got this green force of T1 cos 30. Yeah, let's call it the left positive and then minusing my T2 cos 45. That's giving me 0, right? Because they're the only two forces at play. There's no gravity acting horizontally. Once again, you know what? I'll move this guy over and then sub in the exact values at the same time. That guy there is root 3 on 2 equals a T2 root 2 on 2. So if I made T1 the subject there, the 2's cancel out. You sort of get root 3 downstairs. So it'll be like root 2 on root 3 T2. And there is my second equation to solve simultaneously. So obviously, it looks like I'm just going to basically plug this guy, sub that into this guy here, and then make T2 the subject. So see if I have enough vertical. Oh, heaps of space. So sub 2 into 1. And let's see what we get. So root 2 on root 3 T2 plus root 2 T2 equals to 392. Factorize the two T2's out. Root 2 on root 3 plus root 2, and then mathematically divide it over and punch it in your calculator. Yeah, I believe if you did that, you get 175.7 newtons. Yep, and if you sub this guy into this one, you would find the value of T1 to be 143. Oops, that was the bottom of my page. 143.5 newtons. How's that? Yeah, so in this case, we basically identified that there's some diagonal forces. So we then resolve the verticals to line them up and resolve the horizontal. So what you'll see, especially in the next questions when we start doing inclined planes, when you start having diagonal and vertical forces, you have one of two choices. You either make all the diagonals into vertical and horizontal, like this one here, because it's easier, I can see it, or you turn it into the vertical, the diagonal forces. So I can, in this case, if it's easier, I can re-express mg in the directions of T1, T2, but because it's not a nice right angle here, I made everything vertical, right? In the next question, you'll see that when there's nice right angles, sometimes it's easier mathematically to go diagonally. Yeah? So hope that's okay. I'm going to now do two inclined plane questions, which one's stationary, so it's actually fairly easy. The next one after that has a pulley system which has acceleration, so a little bit more, but not too bad. Hopefully that's okay. Still not on. So this one has an inclined plane. Yeah, or sometimes in the old 4-unit language, they call it a banked track. But for us here, just looks like this, right? Example. So let's give an example where, well, maybe that's a bit too steep. So a bit less steep, just so we can illustrate the point. Let's bank this track at 30 degrees. Let's say there's an object, right? And currently the object is sitting such that it's stationary. Now, how's that so? Basically, the friction is on this surface is so great that it's unable to slide down, right? So what that means is there is a friction force dragging it upwards, right? Which offsets gravity pulling it downwards. Now, there's another force that they call the normal force acting on here, right? Which is basically the force that is exerted by the surface onto the object, right? To counteract gravity pushing. So basically, it's Newton's third law of equal and opposite reaction, right? There's a force pushing down onto the surface exerts a normal force back onto the object. So they're the two tangible forces, right, that are acting on the third one is gravity, but it's generally not given in the diagram, right? So in this case, if I said to you, if everything is stationary, so let's picture this to be stationary, A, E, yeah, stationary. And the question says find F and N to 1 dp. All right, classic. So the fact that it's stationary makes life a little bit easier, right? Because if it's stationary, FA is 0. Oh, sorry, MA is 0. Yeah, acceleration is 0. So now in this situation, I have a choice. I either create vertical and horizontal forces from the F and N, which is a bit complicated. A very quick way to do this actually is if I set up a gravity force, right? What I'm going to do is I'm going to because this is at the two normal and friction forces are at a nice sort of right angle, right? There's a nice right angle to them. Yeah, nice right angle. It makes my life a little bit easier because I'm going to decompose the green force into a force that is parallel to the surface, so it lines up with F, and then there's one that's perpendicular to F or the surface, which is parallel in the direction of N. That makes it easier. So in other words, I'm going to decompose this green force into an element that looks like, oops, so I'm trying to draw it nicer. One that goes like this, and then the other one sort of goes down like that, right? So basically the one that goes across here would be offsetting with the F to make it 0, and the one going down this way would offset with N to give 0, and both of those equations will let me solve for F and N, right? And what I haven't given you in the question is what the mass is, so let me quickly do that. Let's assume that the mass was 8 kilograms, right? Just to make our lives a little bit easier, so 8 kilograms. All right, so then the only thing you'll have to do is, in this green triangle here, I need to find an expression for the top vector and the bottom vector as I decompose it, right? That's a right angle there. Now, whenever I draw this diagram, I don't want to draw any more in there. I want to show you how I get the angles all lined up. So let me just draw this a little bit longer. Yeah. Now, the best way to sort of see it is picture the object as a dot, right? And then I know this is 30 degrees, and I know that there's a number of things at play here. Also, there is a normal, oops, I totally missed the point. Normal force there as well. Yeah. That's normal. Picture that force there to be frictional. Yep. Now, where's the triangle at play here? Picture the triangle at play to be, that's the downward force. This guy here is my triangle, right? This one here. That, right? So where's my angle? So using alternate angles, I know this is 30 degrees. Since this is a right angle, I know this is 60 degrees. Yep. Because this is a right angle inside the green triangle, I know this is 30 degrees. Yep. So basically by using two sets of complementary angles, you'll get that this bottom angle here is 30 degrees. Now that's nice because if I was to draw that triangle a little bit larger just so I can see it, right? It sort of looks like this. There's a straight force down, there's one that goes across, one that goes here, right? This straight down is mg. Yep. And this is 30 degrees. That's obviously a right angle. Then I know, right? I know that this guy here being mg, then this one here would be SOHCAHTOA using sine. It will be mg sine 30. And this one here would be mg cos 30. Yep. Great. Once you understand that, then I basically would match up this guy with the F and then match up this guy here with the N to basically get my value. So I'm going to call the green ones parallel to surface, right? Comparing those forces parallel to surface, I know that this guy minus this guy should give me 0. So basically F equals to mg sine 30, which subbing in my values there would be 8 times 9.8 times the exact value of a half, 8 times. So what's that? 39.2 newtons. Oops. Pretty straightforward. And then perpendicular forces to the surface, the blue forces here, I know that N equals to mg cos 30. So the same exact calculation with root 3 on 2. So $67.9 newtons. How's that? Not too bad. So these are my two answers. So it's really important for you to be able to decompose forces to align them. In this case, I aligned them to the F and the N because diagonally because it's a nice right angle in between, and it just makes calculations easier. Now you can try to align this vertically and horizontally, but it means you have to decompose N and F, which is a bit of a pain. And if you try to do it, you'll see that the simultaneous equations that you have to solve, a bit of a pain. That is a much cleaner solution. Guys, let's do one more question. Yeah, hopefully that's okay. Yep, hopefully that's okay. Let me zoom in here. So one more question, which is also a bank track or a inclined plane, but let's put a pulley system onto it, right? Just to give it a bit more forces at play. So picture a pulley system that basically has a weight on this side, suspended in air, and it's then also sort of pulling a mass down here, right? Now, for this purpose, let's say, maybe I drew the sizes of the boxes wrong, but let's say it's not to scale. Let's say there is an acceleration downwards, right? So theoretically, you can have an acceleration going the other way, right? The calculations are conceptually the same. It's just everything sort of minus, right? Where let's say the net acceleration there is 4 meters per second squared, right? What else can I give you? Let's say this is a 3 kilogram weight, right? Let's say this is a missing mass of capital M kilograms. And let's use uglier numbers like 40 degrees, right? So we can't use exact values. Now, in the question here, because it's a common string with no mass, let's call it tension and tension, right? Same tension because it's connected. It's a connected string, it's the same string. And obviously, so in this case, friction, let's assume no friction, and friction is in fact replaced by tension, and there is normal force, but what you'll find, and I'll label it for you, not that it matters, the normal force is actually irrelevant in this question, right? The relevance of normal force was in the previous question. You can find it, right? You can find the value of normal force, but it has no bearing on the way this question is going to play out, because in this question, I'm going to ask you to find the tension, and I'm going to ask you to find the mass, both of which, if you find a tension, you just need the forces parallel to the tension. And once you find tension, you can use and find mass using gravity, right? Normal force is just not a thing. So you know what? For this question, I'm just going to leave it out. Yeah. So this question here is find T and M to 1 dp. Yeah. So when they don't give you the normal force and it's not asking the question, ignore it. You don't really need it all the time, right? So in this case, then it's clear. I have an invisible right now gravity force, right? Which once again, in fact, let me make this a little bit longer, right? I'm going to decompose that into that is parallel to the surface, which is the one I need, and perpendicular, but I don't really need the one that's perpendicular because there's no normal force at play. So what I'm going to do, basically, I know 40 degrees, using my alternate angles, there's 40. that's 50, and that's 40 again. So I know it's going to be this angle down here. Right, the more times you do it, the more times you sort of see that happening. So you sort of remember. So this force down here, right? This one here is the one that I want, and that guy there is mg sine 40, right? So I can equate that mg sine 40. I can equate this force to this force. And then once I find t using that equation, now when I say equate, I don't actually mean like that's equal to that, because there is acceleration. So the net force equals to t, because it's moving in the direction of t, minus mg sine 40. Use that to find t. Once you find t, use the ma on the larger mass to find acceleration. And right now what's missing here is that there is a missing capital mg there as well. So there are two sets of forces at play, one here, one here. I'll do the green first and then use it to find the blue, right? So let's do this. So on the block, yeah, using the forces parallel to the surface, I got ma, so my resultant force equals to t, because it's traveling up here, right? Minus, yeah, if t is positive, so if we're traveling up the bank track or up the incline plane, then t is positive and mg sine 40 is negative. What am I trying to do? I want to make t the subject, right? Yep, so then in this case, t equals to ma minus mg sine 40, and I have all these values, right? I got m is 3, this is 4, minus 3, 9.8 sine 40. Right, punch in your calculator. What'd you get? 30.9 newtons. Yeah, for the value of the tension. Pretty easy, right? Once you understand that there is a net force, a net acceleration, that becomes your direction, which dictates which one's positive. T is positive, and the one going down, gravity, parallel to the surface, is negative. Yeah? Once you get T, let's look at the box, right? So vertically, there is no horizontal forces on here. Vertically, I've got, now, once again, MA is pointing downwards, so this is capital M, oops, capital MA equals to capital MG minus tension, right? So I need to make capital M the subject, so what I'm going to do, I'm going to move tension over to this side. I'm going to move this guy over here and factorize it. So it sort of becomes like tension equals to capital M G minus A, right? And then all I got to do, sub in tension into here. That's 30.9 equals to mass still missing, 9.8 minus the acceleration of 4. Divide that over. So once you get that, you should get 5.3 kilograms, right? As the missing mass. And that's it, guys. Right? By resolving forces, this is how you do this part of the topic. It is considered to be hard. Some people get this, like, because they do a bit of physics, or it's not too bad, and that's great, because between this and projectile motions, application of vectors is, in my opinion, the hardest part of extension 1. So next few lessons, I'll be covering projectile motions. Hopefully you'll tune into that. If you like this video, please give me a like, subscribe, tell your friends. I'll see you guys next time.